All right, folks. So here we are. So I thought in the PCA chapter, we're about to look at how to do maximum likelihood estimation of the parameters using expectation maximization. And because we've jumped ahead to that chapter, I thought it would be useful to have a little kind of a crash course in expectation maximization, what it's all about, so that so you'll know what to do and why we're doing what we're doing when we talk about it in the context of PCA. Now, expectation maximization is a very powerful algorithm. You'll see it all over the place. But I found that when I first learned about it, it just seemed a bit mysterious. Like I could kind of follow the logic of it, but I didn't really feel like I understood it. And I got a better understanding of it when during my kind of first postdoc, my advisor told me about this other view of expectation maximization as coordinate ascent on a lower bound of the log likelihood. So the thing we're trying to maximize, we actually end up forming a quantity that's a lower bound. And now it's got two knobs that we can turn. And expectation maximization ends up being us alternating, turning one of those knobs and then the other knob and working our way, laddering our way up and producing better and hopefully better estimates. And I've just always found that much easier to understand. And it's got much that view I found helps me understand kind of machine learning algorithms much better. So I thought we'd discuss it from that perspective here. And then later when we go back to chapter 9, where I think EM is covered in Bishop, we'll go through it again in more details there. But I thought it would be good to do a little mini course on it now. Okay. So as I said, so we're going to be talking about understanding expectation maximization as coordinate ascent. So that's kind of the game we're going to be playing. Now, as I said, so I learned these from my first postdoc advisor, who learned them, I believe, from this good paper by Neal and Hinton from 1998. So have a look at that one. It's quite readable. There's also a discussion of it in Roweis and Garamani. And chapter 9 of Bishop, in particular, this section actually does cover it as well. So the material is kind of coming sort of from all of those places, and I've got references at the end, so you can look at it. Now, these notes are also on my blog, so you can, I'll link to them so you can have a look in detail there as well. Okay, so let's get into it. So what are we trying to do? Well, we're trying to do maximum likelihood estimation of parameters theta, explaining some data. So let's kind of just highlight that with some parameters, giving some data. Okay, so this is the thing we're trying to solve. And often, well, I don't know, but a lot of the time, it can be useful to introduce hidden variables and consider the joint distribution. So instead of considering this, let's say the marginal distribution of the data, maybe consider the joint distribution with those hidden variables. So that's going to be, an important, essentially EM is for doing maximum likelihood estimation in these settings where you have hidden or latent variables. Hidden and latent mean the same thing. Okay, so introducing hidden variables, that's going to be kind of the key step. Okay, so now I say, there are a variety of reasons why I would consider doing this, and sometimes, it's going to be representing missing data. And I think, in the initial context that I came across EM, it was in that setting that those hidden variables are actually data points that you're missing, and you want to kind of infer those values. And the way you kind of go about doing it is kind of natural. You would say, well, what if I just filled it in? I had my parameters. I'll just make some guesses of the parameters, and those parameters, then I will use those parameters to kind of guess what those values are for the missing variables. And then I'll use now my new complete data set to go back and then update my parameters, and hopefully just iterating that back and forth, I'll get at I'll end up at a good place and a good estimate. So the question is, why does that work? And how do we do that properly? And that's kind of what this is all about. Okay, so sometimes Z are, let me put on the highlighter here. So sometimes Z are missing data. So which, if we knew, would make the estimation problem easier. And then there are other times, and these are the settings in which I've worked with it most. And I think this is probably a setting that comes up a lot in machine learning too, is when there are actual hidden kind of causes in the world that are producing these observations. So these X's that we're talking about here, they're let's say your sensor readings, right? You don't know what objects are in your environment, but you have sensor readings, and what you want to do is infer. You want to infer the parameters that are, for example, going from those objects to your sensor readings, or you want to kind of figure out, what objects there are, etc. So, sometimes it's not just hidden data in the sense of, well, I'm missing some sensor values. It's actually like, I have all the sensor values, but I can explain them better in terms of, objects in the world that I don't observe directly and I need to kind of infer. So that's kind of another setting in which it can be very useful. So Z represents causes that have generated our observations. Okay? And then sometimes it can just be for purely computational reasons. Like maybe it's just, you can get a better estimate. Maybe it's easier to estimate it if you kind of guess some distribution on Z and work your way up. So either way, we're going to introduce some, latent variables into the problem. And now how are they going to kind of make our life easier? So, if we just kind of try to kind of incorporate them naively, like it doesn't seem to work right away, right? So we say, well, we've got this log likelihood. Well, okay, I've got my new latent variable, so I can try to express this log likelihood as a marginalization over this latent variable. But that doesn't seem like it doesn't seem to have kind of made our problem super easy right off the bat. So especially because this integral, if it was outside, life would be good, but it's actually inside the logarithm, and that's that can be makes life hard for us. Okay, so we're going to kind of take a different approach and see how to use Z in kind of a slightly different way. So the expectation maximization algorithm, so as you might have come across it, like I think it was developed in the 70s or something like this. So back then they say, okay, well here's some procedure, just do this, and we don't know why we should do this. And in this, I mean, of course they explain it in the paper, but it just never really kind of stuck for me. But anyway, here's a procedure, and we're gonna talk through it, and then we'll see that we actually end up with exactly this procedure in somehow kind of maybe a more principled way. Okay, so what the procedure, the EM algorithm says, you've got a previous estimate, so your previous guess at the parameters, and we should first compute the expectation. So this is kind of the expectation step. So what you do is you've got this joint distribution, and now you compute the expectation of this joint distribution over Z, given the previous value. So given the posterior distribution on the latents, given your previous guess. So now you've got this quantity, right, which is now a function both of your previous set of your previous parameters, and now is also a function of theta because it's showing up here, right? So you're essentially you're taking the average of the joint distribution over Z. Okay, notice we're taking the average on the outside, not on the inside. Why is that a good thing to do? It's not clear, but turns out, so if we maximize this distribution now with respect to theta, so we've got our old parameter, so we've got just a single parameter here, we maximize it, we're guaranteed that this procedure doesn't decrease the log likelihood. It'll often make things, increase the log likelihood. Things work very well. So the question is, why does this work? The original papers do, of course, describe this, but we're going to look at it from kind of a different perspective. So that's what I say here. The motivation behind the algorithm and why it works we're always a bit mysterious, but we can actually view it, EM, as coordinate, should be actually ascent, on a lower bound to the log likelihood. So in fact, it turns out that this quantity ends up being kind of a lower bound to the log likelihood, and it's easier for us to maximize. So we just kind of maximize that, and we hope that we are getting also better parameter values for the problem we care about, which is the log likelihood itself. Okay, so that's what we're going to talk about. And the very first step is, okay, forming this lower bound of the log likelihood. And how are we going to do it? And the way we're going to do it is we're going to use a couple of steps that seem like a little bit trivial, like why would you arrange things in this particular way? But when we combine them, it's going to give us a powerful expression for the log likelihood. Okay, so just going to bear with me here as we go through these steps. So for any, let's say, so we've got Z, our latent variables. Now for any probability distribution on Z, we have the following, right? So the log likelihood, no Z's in it, is the same as 1 times the log likelihood, of course. Now 1 is just the same as the integral of this of the distribution. And because this distribution doesn't depend on x, we can just bring it inside, right? So we can actually write this as, okay, so kind of just coming under kind of a trivial average of the log likelihood. And then on top, okay, so this isn't really helpful, right? Like, the whole point is we want to manipulate the log likelihood itself. So we're going to add in another kind of trivial step, and we're going to say, well, the log of p of x is the same as the log of p of x times 1, and 1 is the same as q of z over z. Okay, again, it's not clear what we've gained. So now, previously we tried writing this in terms of the sum rule of probability, which was the marginalization. We tried to write p of x as some integral, but that wasn't very useful. So why don't we try the product rule, and we actually write this using Bayes' rule as a ratio of the joint distribution to the conditional distribution, right? So if you actually bring this up to the top, this is just another way of saying, this is the same as, this top part is the same as pz given x theta, px given theta. So we've just kind of rearranged that. So now we're kind of in business, right? So now we can actually, there's some kind of non-trivial re-expressions here of what we got. So now we get a more interesting distribution. We've got the qz that was multiplying log of the log likelihood, and now we've expressed the log likelihood in terms of z in kind of an interesting way. We've got this ratio here that is going to be the ratio explaining p of x, and we've got these two guys hanging out. And now all we do is we expand out this logarithm term, and we combine terms in a particular way. And there's actually so if I recall from variational autoencoding, just a little bit of an aside, you can combine these terms in different ways. So the way we're going to do it for EM is one particular way, but there are other ways of doing it. Okay, so we're going to do this. We're going to do this in a particular way. So first, we're going to take q of z, and we're going to combine that, and that's going to become our expectation with respect to q of the log joint distribution. And then we're going to take q of z and that guy, and that's going to give us an entropy term. And then all we have that's left is this q of z, and then it's going all the way up to here and here. And that's going to give us a KL divergence. Okay, so now, so the next step we do is we just combine these two terms. So on the left side here, just make sure we've got, this is sitting log p of x given theta. So we're just writing an expression for the log likelihood. And now we've said, well, if we pack this quantity into, give it a name, it's the negative variational free energy for reasons that come from physics. We're going to pack it up like this. It's also known, I think more recently it's started to be known as evidence lower bound, because we can also write it as, we can just take this to the other side, and we can write it as the log likelihood minus the KL divergence. And because this thing is always greater than or equal to 0, this quantity, the ELBO, is actually a lower bound for the log likelihood, which in some settings will also be known as the model evidence. So it's kind of it's lower bounding log likelihood, equivalently lower bounding the model evidence in this setting. Okay, so that's where the name comes from, the ELBO. So I'll talk about it as the ELBO because negative variational free energy is a bit of a mouthful. The main thing is we've expressed the log likelihood as this variational free energy, or the ELBO, plus the KL divergence. Okay, so this quantity is like this super, it's the star of the show, very, very important. Okay, so that's a good, and now we can talk about expectation maximization as coordinate descent. Okay, so now we've got a lower bound to the log likelihood. We can maximize it and hope to improve the log likelihood that we're after. But now f of this ELBO is a function of two variables, so we can perform this maximization using coordinate descent, going up on one, then maximizing the other, and hopefully we get to a good place. Notice that it's actually a function of a distribution, so q is actually a distribution, and theta is our normal parameter. So they're kind of different types of things. But that's fine. Okay, so how are we going to do this coordinate descent? Well, this is kind of the next cool thing. So we're going to use the fact that we've actually got two different expressions for f of q theta, right? So we've got this initial definition. So let's write this as I'm in the middle. Great. Okay, so we're going to call this expression 1. And then we've got this second expression here. So let me actually erase some of this stuff. Okay, so we're going to highlight two things. So this is one expression, super important. And then this is another expression, equivalent, right? Super important. Okay, so this is number 1, expression 2. Both of these are useful. Why are they useful? Okay, well, it's because it's because when we want to maximize we want to maximize with respect to Q and respect to theta, right? The distribution and the parameters. Well, if we want to maximize with respect to the distribution, we can use this expression, right? Because it's got two terms, but the log likelihood doesn't have Q in it. So all we have to do is deal with this one. And if you want to maximize with respect to theta, well, all we have to do is deal with this side. And so it allows us to kind of alternate two processes, minimizing this, maximizing that. And that gives us kind of the expectation and maximization steps. Okay, so that's exactly what I say here. So to do so, we leverage the two different expressions for f of q. So let's highlight this that we derived above. So notice in the second one, the distribution q only appears in the KL divergence. So that's what I'm saying. So q is only showing up in this KL divergence term. Okay, so given the previous set of parameters, we can maximize the ELBO with respect to the distribution by maximizing this expression. Well, what does that mean? Well, that means minimizing the KL divergence. Okay, right? Because q just is not showing up in the other thing. All we can do is minimize this negative term. And so we arrive at the E step, right? Because the KL divergence is going to be 0, which is kind of the smallest value that it can take, when this distribution equals Q, if and only if. This in turn means that, so minimizing the KL, which happens when the two distributions of divergence are equal. So that gives us our E step. So we've got our previous parameters, and we set Q of t, so as a function, to be the posterior given those parameters. Okay, so that's the E step. We're going to set our proposed distribution on Z to be the posterior on the latent variables given the previous set of parameters. So this is kind of like what we're talking about intuitively at the beginning, right? Like we've got some old guess at the parameters. Let's set the latent variables to like something like some summary of their values given those guesses, the parameters. So instead of summarizing, we're just taking the full distribution here. We've got we want to know what z is. Well, let's just take the old parameters, plug them in, and get a distribution over z. So in the E step, we just do that. We said, okay, our distribution is the posterior on those latents. So our best, best guesses, we're not really guessing, but our state of knowledge about those latents, given the data and our previous set of parameters. Okay, so at the end of this E step, the KL divergence has been reduced to 0, and the ELBO equals the log likelihood, right? Because from this expression, we've just set this to 0, and we got parameters t minus 1, I guess, t minus 1. So the log likelihood, we've actually matched the log likelihood. So as long as Q is powerful enough to be able to capture your posterior distribution, you can set it to match the posterior given for the last set of parameters, and this expression will hold. So let's highlight that. Okay. Now there's in Bishop, he actually points out that there's actually even a stronger property, that it's not just that the two curves, for example, touch as a function of the parameters, they're actually kind of tangent to each other. And there's a derivation here. I go through why it is. You can go through it. It's very straightforward. But shows you, and you'll see it in the picture what I mean. But it's a simple derivation. We'll skip that for now. But it's just kind of cool to know. Okay, so now we're get to the M step, right? So we maximize with respect to Q, and now we want to maximize the ELBO with respect to the parameters. So there we go. So what do? Well, we're going to maximize this variational distribution now with respect to theta. Okay, so and Q is now going to be set at its distribution given the previous set of parameters, right? So now remember what we had? There was like a h of q hanging out here. So we're going to use the second expression. Sorry, we're going to use the first expression, this one now. And now q is now, it's using the previous set of parameters. So theta, the thing that we can now update, only appears here. So there's the stale theta showing up in q, and now we're going to update our parameter. Okay, so this should say, using the first expression. Okay? So I'll put that in the block. So it's important that we're using the two different ones. Okay, so we're just going to maximize this. So that's kind of maximizing with respect to the posterior distribution on the latents, the log joint. And so I actually spelled that out explicitly, and it turns out this is exactly what we were supposed to do in the initial recipe for EM. Okay, so it turns out that the original formulation EM is equivalent to our coordinate ascent perspective. And so the reason why you do this is because we've essentially added one additional step, which is letting Q be this kind of free parameter that we then set to be the posterior. And it turns out that this then kind of opens up this whole maybe you can't do this, or maybe there's you want to approximate some other ways. And that opens up this whole interesting area of like variational EM and using this better distributions or simpler distributions, and then what happens to how well can you estimate things, and etc. etc. So the old the EM as it's presented corresponds to settings where you can actually match exactly that posterior distribution on the latents, but in many other interesting cases of application machine learning you can't do that, and then you have to deal with them in a more careful way. But as far as EM is concerned, and as for our application into PCA, we're going to assume that we can do this, and we end up at the exact same procedure as we had before. And now look at how that EM doesn't decrease the log likelihood. Notice that we've got the log likelihood of the previous set of parameters, which we said was equal to because of the way we could set Q arbitrarily to what we needed, to the ELBO, and then the M step we actually increased, hopefully, but we certainly didn't decrease the value of F. Then we do another E step to now update Q again, and now this is going to equal to the value of the parameters, the log likelihood at the new set of parameters. So at each one of these steps, we're not decreasing log likelihood, and hopefully we're also kind of increasing it. Okay, so, and one final point is the inequalities will also hold if we merely increase rather than maximize in the M step. So you don't have to do a full maximization, you're just going to increase your theta by a small amount, and all of this will still hold. Okay, so that's kind of basically what EM is about. Let's just have a little picture of it. So here is this nice picture from Bishop. So here is, we've got the log likelihood, this complicated thing, as a function of theta here. And now we've got he's called it L. So this is our F function at the old parameter values. And notice that it's touching. So these are our old parameters. So they're touching and they're tangent. So now we do the M step. We figure out, okay, we maximize this thing, and now that gives us a new parameter. So let's do M step, E step, and then the E step we get a new distribution that now is still lower bounding and is now tangent at a new location, and we just keep going, and hopefully then we end up there. I don't think there's a guarantee that you will. Not sure about that, but either way. You are at least not decreasing your log likelihood. I think in some settings you can say that you actually converge to at least a local maximum of the log likelihood. So if you can actually do this full E step, then I think things are pretty good. But I'll have to double check exactly what holds there. Yeah, so that's about it. So I think essentially what the whole point of all this was doing maximum likelihood estimation in models of latent variables. And so we had this kind of prescription for how to do things, and we saw that you can actually view this as doing coordinate descent on this expectation lower bound. The evidence lower bound. So here is that, using these two expressions. So I think these are like really important. When I learned this stuff, I spent like every day almost, I would just rederive this just to like make sure it kind of just went into my brain, and it's just super useful. It's been very useful for me throughout, and I see it popping up all over the place. So this is something you should definitely know about. So this is basically using these two expressions to maximize with respect to Q and with respect to theta. Okay, so in the E step, we just set Q of t to be the posterior, and then in the M step, we maximize the parameters. And doing so, we're guaranteed not to decrease the log likelihood. And I have to double check this and look it up, but I believe under some settings, you'll even go to a local maximum of the log likelihood even. So This is just me being very conservative, but I think you guys should do better. Okay, here just kind of some reference at the end. And so I hope you find that useful. Again, I think this EM stuff is extremely useful, something all machine learning learners should really know about and have solid. So I hope this video helped you understand that a bit. And the next time we'll apply these ideas to looking at maximum likelihood estimation of the parameters in PCA using EM. So hopefully I will see you there. Bye.